some patterns did not become theorems, and there will be open questions too. So, bonjour les enfants. Good morning and buen día. So, well, this talk, is my deepest intention that it will be understandable. Please, please, please stop me, ask questions, or speed me up if needed. This should be relaxing and understandable. So I have an enormous plan, and yeah, I know. I mean, I don't have a good timing, so probably I'll do 1, 2, and 3, but whatever. So let's see. Let me start. Let me put my things in order. So this is a pair of pants of a very strange person, and I like to understand curves in the pair of pants. And to understand it, well, sometimes it's good to flatten it, and then I'm going to cut it. And the rule for the cuts are they're going from boundary component to boundary component. They don't intersect each other, and they can go from a boundary component to itself. And I want to put as many cuts as I can without disconnecting whatever surface I have. In this case, it's a pair of pants, and of course, as I said, cuts not cutting each other. So then I open up and I keep a memory of who's glued with who. Here you have two indications, colors and letters, and there's uppercase and lowercase that will play a role later. By the way, you see a capital B, and this in your mind should look like a bar, A bar or B bar or inverse, but it's much more painful to put that in the computer, so I use a capital letter. So I open up the pair of pants and I get a polygon that has every other edge labeled. And since I know what I did, I know if I glue the edges, I will recover my surface. So then I can read the letters in circle. Sorry, I'm looking, no, this is, oops. Here we are. So I read the letters. So here is A, capital A, B, capital B. And this is a surface word. And it's like a recipe to encode this particular surface. It is a recipe, not like a recipe. Now we have this is a torus with one boundary component. And so here, the cuts, slightly more complicated, we know them, and here is the open up polygon. And the surface word is AB, capital A, capital B. So here we have the two surfaces that I introduced to you, and their surface words. And the wonderful thing is the surface words know all the secrets of the curves on each other, on themselves, and they're going to tell us the secret. So now we're going to look at curves. So now the surface is fixed. Surface fixed, surface word fixed. So I'm going to look at curves on the surface, and as you see, I do two particular curves in the pair of pants, which are, the curve, well, labeled by B. Why do I label by B the green curve? Well, because if I start, these are directed curves. So if I start at any place or run around the arrows, I land, first I touch the B, the segment on the small b side. This is the word I'm going to remember. This is a word of one letter. And we have to think of this word as a ring of letters. So B is a ring of only one bead. Here I have another one, so we can see. So I start here, and I start wherever I want to, because this is a ring. So here I start here, and I hit small a. And of course, we're all so smart. So, I feel the small a sector, say, and then I go to the capital A. I'm not going to record the capital A, but because I know that every time I hit a small a, I'm going to go to a big A, so I just go. So A, go around, B, and then go around, capital A, go around, capital B, and I'm back where I started. So that's my ring. And this is a curved word. This curved word depends on the curved surface I chose first. So let's fix those, and you can probably, if I ask you for a definition of a surface word, you can tell me, it contains a certain amount of letter. Since I have to glue pairs of edges, if it contains a lowercase, contains an uppercase of the same letter, and vice versa, and so on. What are the rules of the curved words? They are totally different. And, one rule is that, well, I'm not going to allow my curves do inefficient things like, for instance, here I have this thing that goes capital B and then small b. I don't have these fingers crossing an edge. I make them tight. So the cyclic words, are reduced, the curved words. So this is only a rule for the curved words. Okay. And let's see what comes here. So I have a free homotopy class. I have, again, surface is fixed. I have a free homotopy class. I have a closed directed curve on a surface up to the formation. That's a free homotopy class. And then, one can look at it as a conjugacy class on the fundamental group of my surface. One can look at it as a cyclic reduced word. And, my surface, in my two examples from now on, will always have boundary. So we have a one-to-one correspondence between free homotopy classes and cyclic reduced words. You can work around that, but if you want this nice one-to-one correspondence, you need that. And as we also saw a few times, we have a unique geodesic in the free homotopy class. Now, I should hear some complaints now. Let me see if I said this, but I have this word. This word depends on the choice of my surface word. So this is always fixed. And I have a geodesic, of course, if I have a nice, I like constant negative curvature. So if I have a constant negative curvature metric on the surface. So those are choices we have to make a priori before getting these things. So once I have a free homotopy class, one thing we have is the self-intersection number of that curve. And this is the smallest numbers that the curve, in which the curve crosses itself. And I always count double crossings. If they are triple, I wiggle the curve a little bit. And one triple will count as 3. Then I have the word length. And this is just the number of letters that the word representing my class has. And then I also have the geometric length. And again, this is the length of the geodesic in my chosen favorite metric. And all these numbers, these 3 numbers that I can associate with the free homotopy class, can be computed. There's algorithms to compute it in many cases. And this is what I'm going to do. And then experiment and see relations between these 3 numbers. So for intersections. So here I have, this is a nice curve on the torus with one boundary component in purple. On purpose, I kept the cut that I did on my torus. Oops, I didn't mean to do that. Anyway, let's just, so that, if we go very slowly, you will see that this word, you have to trust me now, has this cyclic word associated to it. And here we see why it's nicer to cut it. In the pair of pounds, since I can put it flat, it can be understandable just by looking at their actual surface. In this case, the cut will help us. And I'm going to look at the intersection, the self-intersection points. So you see here, I marked 2 branches. Sorry. But let me go. Okay, here it is. This point here, it's in these 2 pieces of curve. And, I asked myself, why do I have that intersection point? Well, because I am going from the segment level, by, capital A to the small a in this piece of curve, and small b to capital B in the other piece of curve. So why do I have those segments, those pieces of curve in my big, whole curve? Well, because I'm going from, let's do this one because it's easier. I'm going to small b because here I enter through big B, when here I went to big B again. So I have a BB in my curve word. So I have a capital B, consecutive in my word. I will have a segment like this, no matter how the curve word is. Same thing with this AA. This AA corresponds to two small a's going together, and it could be this one, this pair, or this pair, and I can quiz you at the end which one is it. So every time I have a word that contains capital B, small a, no matter where in the curve word, I will have an intersection. In fact, every occurrence of such a pair will give me an intersection, a self-intersection of the curve. So this is in a nutshell a good picture to remember, to compute self-intersection. This is not all of it. There's always a little more, but the little more is really, here is the essence of the algorithm. So here are the two words marked, and I write the cyclic word as linear because writing cyclic words is quite painful. Here there's another one, and well, where are these? This one is here. Here I have, I look at another point in red, and this goes from capital A to B, C to B, and capital A to small a. Now these two, well, a priori I don't know whether they intersect or not. These are two segments going like this, but they may do like this. So, well, to know what happens, one has to go to the past. I'm going to follow and see where these two come from. This one comes here, goes to small b, and this one comes here. So in this case, I start, one curve starts at small b and the other one at A, and they go together to the capital A. No, they go together to small a, they cross there in the capital A, and then they do like this. So this tells me intersection. And it's easier to see this picture, though this is the past, but it's easier to see this picture like this. So the one we discussed before looks like, well, like this one. In this case, this is a different one. One more, like I could start in two different cuts, go to the same, and you can go to the same for 1,000 letters, and then either you do like this, and you have an intersection, or you do like this, and you don't. And only depends on the first and last picture, what would happen. So you can have a situation like this, which is what I just described. You can have the same situation, but the two curves point in different directions. And you have to keep that in mind, or just the thing like this that we discussed in the very, very beginning. Any question? Okay. So, oh gosh, I think I'm going backwards. Nope. So here is a theorem that was proved in stages. Birdman series proved that use this idea to show when a curve is simple, just looking at the word. Look at extended to cuts of intersections and self-intersections. At the C's, well, I give it the form you see now. It's not a different algorithm, but it's easy for me to understand because you always understand better than the things that you thought. Basically, this says that if you have a curve that intersects in the minimal possible number of points, there's a one-to-one correspondence between the self-intersection points of this representative of your class and these special pairs of subwords. So there's a list, if you give me a surface word, there's a list of pairs. So when I look at, my curve word, I find how many of this list of pairs contains, and that's the self-intersection number of that class. Okay, so now all of this, as you know, can be input in a computer, so this is what I did. And I make this table. So here, this table contains in the row 2 and column 1, say, how many cyclic reduced words or free homotopy class, and I ask for non-power words, and I'll tell you why probably later, with self-intersection 1 given by the column and number of letters given by the row. So this is the table when it starts. So for instance, well, self-intersection 0, they are the 4. Here we are in the puncture total. So these are the, the usual generators and their inverses. this is a, diagonals are inverses, and so on. So this is a table with the counting. And well, since this is quite painful to do by hand, but the computer did it quite fast. This is a table how it continues, and mathematicians' heart usually dance when they see patterns. You start to see patterns here, and and here there are the pattern continues, and here it is, and here just a reason that the mathematical God tells us non-powers are not the right thing, because if I include powers, look, I have these islands of zeros that don't look as pretty and patterny like as they should. So one more reason not to put patterns. Here is again, and here is again a table. You should memorize all the numbers. Now, but instead, maybe I did this painting, so black means 0. Here this is my table. Black means 0. Yellowish or light yellow means there are few, and the darker the color, the more curves I have. So here you see, for instance, like here we have a nice curve, and if you look at it like this, it's a parabola. We see also that here there's, in a row, we see now because, well, the numbers grow exponentially, so the only row that we really see things is here, the last one, but it starts with very little curves to self-intersection 0, then it grows a lot in the mean self-intersection, and then less curves. So here is a row of the table, the row number 8. So again, these are all the free homotopy classes that I can express with a word of 8 letters. And I'm going to do a histogram. So I'm going to put a rectangle over each square with a height proportional to the number of curves I have there. There it is. And there is the histogram with more letters. So here is the mathematicians, frenetically dancing. So this is, words of length 20. And then what I did is, well, there was a Gaussian. And, I like probability, but I'm not that good at it. So I had to go and, go to the weird spot in the School of Athens. And in my case, this was Steve Lally. And I wrote to him and I said, he's a probabilist, but he had worked in many problems relating geometry and probability. And I said, look, I think this distribution, the self-intersection sampling by word length, gets closer and closer to a Gaussian when the word length grows and grows. And he answered, I don't think so. So I sent her the picture before, the perfect Gaussian that I got in the previous slide, and he answered, let's prove it. And we did. So we proved that the self-intersection number of curves, is a Gaussian. We compute the mean and the standard deviation. So the mean is a constant that depends only on the Euler characteristic of a surface. So for instance, in the case of the torus and the pair of pans, the Euler characteristic is -1. So the mean is 1/9 times the word length square. And the standard deviation is this very complicated formula of the Euler characteristic. So here it is, the theorem. And I'm going to skip this because I'm going a little too slow, I think. Is that clock right? When do I finish? Quarter past 10. Okay. Okay, good. Good, but I'm still. So just wanted to compare two theorems. So this is, one of the reasons I wrote to Steve Lally in the first case. So he has studied, now, before we're measuring length by word length, number of letters, he studied measured length by, hyperbolic length with a negative curve metric, constant negative curve metric. So here he said that the mean, when the length is very large, is -1 times L squared divided by pi squared times the Euler characteristics. This is in the case of geodesic length. And in our example, what we found is the mean is L squared, L is, word length here, and this formula of the Euler characteristic. So, I mean, it's quite different. For instance, you see that when the Euler characteristic is really large, some of you in the audience told me you like, surfaces, infinite surfaces, or surfaces, with very, large genus. Well, notice what happens here. If I fix the length, well, this gets very small. If I fix the length, but the Euler characteristic is very large, this can get very small. While here, this the other way around. This gets very small, but this one, gets close to 1/3. So it's a different behavior because, even if there's a lot of mirroring the discrete, combinatorial word length world and the geodesic length, well, here is a case where they differ. Having a random curve, a very, very large random curve in word length, we know more or less it will have L squared divided by these constant intersections, while here, like if the Euler characteristic is very large, it will be, if the L is very large, it will be large intersection. If the Euler characteristic is very large, but we fix, if the Euler characteristic is large, it's much harder to intersect in a geometric curve. Imagine that you're really going around and you have a tube, for instance, you have to go back, and that you lose a lot of length and come back. Well, here it just drops sticks on a circle, and those sticks intersect much more in some sense than in a surface with a hyperbolic metric. So, and I just want to mention this because I'm very proud of these students. So now we can do the same game, because I want to say one word about the proof, not just be the rabbit thing, the magician that takes the rabbit out of the hat. It was a little magic, that theorem. So let's do the same thing, but now we're going to fix one curve word, and we're going to study intersections of all curves with the curve word that you fixed. And if you do that, with the table as before, so here, now the rows denote word length. I'm counting, how many I have with a certain word length, and the columns as intersection with this particular curve that I chose. And I gave this problem to a high school student who's very, very brilliant. Now she's finishing her PhD at MIT, and I said, look, I think this is a Gaussian, and she proved it. And here, and I'm sorry, I should have shown you the picture. So this, I mean, it's a little hard to, to count them all, but it looks more and more as a Gaussian as, the word length grows. There's something as before. You can compute, the Euler mean and standard deviation. And the idea in this case is that, well, if I have one of my words fixed, remember that self-intersection is, or same as intersection is, self-intersection was counting pairs of words. Intersection is counting pairs of words, sub-words. One belongs to one curve word, and the other sub-word belongs to the other curve word. Now I have one list of curve words given by my fixed curve. So in the other list, I just have to count occurrences of certain subwords, and this is going to get, so each list in the, sorry, let me just point, I need to point. So this curve word gives me a list of curve words, and each list here has another curve word possible that will give intersection. So I can forget this now. If I have the possible, completion of my pairs here, I just have to count occurrences of this infinite list. But my, in all the words up to a certain curve word. So if you give me all the words, I count occurrences of that. And if I ask you, I'll go and look into the weird probabilistics in the scholastic. If I ask you occurrences of one subword in all the words of length something, what is that distribution? If you pick a word at random, what do you get? Well, the distribution of occurrences of one given subworry would be a Gaussian. And if you ask for a lot, it's also a Gaussian. So in this case, it's just counting subwords. The difficulty in the case of pairs is that counting pairs of things is harder, and there are central limit theorems for that. But you need some very, like my collaborator Steve Lally, who worked this is U statistic, which is something I have to confess I don't fully understand even after a paper is published. So here it is. Okay, so now let's sampling slightly different. So here we did another experiment, and in this experiment, I think I took, youngest and oldest persons in the department. This was an undergrad student, Karen Lee, and a Bernie Maskid, who was emeritus, still emeritus at that time. And what we did is, we look at pair of pants, metrics on the pair of pants, and for each word, we fix the pair of pants, and we fix a metric on the pair of pants. So the metric is given by the length of the three boundary components. So if you don't know, just think of there are three parameters. I think I put it here, a pair of pants. See, the pair of pants should be there. Okay. So a pair of pants, and the length of each of the boundary components, A, B, and C. Here there are three different A, B, and C. Then I look at all. In this case, I didn't look at them all. We did. Sorry. The pointer is very similar to the forward, and I keep confusing them without my glasses. So, so here is the pair of pants of length 1, 1, 1. So I look at all the words of, not all the words, I keep saying that. I look at 100,000 words chosen at random, and they are word length 100. And for each one, I compute the length of the metric determined by these three parameters. And then I make, I make the histogram of how these lengths distribute. And so here is with a metric, which is one boundary component is 10, one is 0.1, and one is length 1, and so on. Is there any question? Thank you. Yeah, so this is a little strange. I mean, you probably read here, we conjecture that this goes to a Gaussian, but this, doesn't look like a Gaussian. And this doesn't look like a Gaussian comes from the big difference. I have a 0.1 and 10. It also comes, I should have said this, of the way I parameterize this, because remember, my words, so I made a little mess. All the three boundary components, they don't have the same status. So remember that my words were in A and B, so there's two boundary components that are preferred. There's a choice there. So even if these two things should look the same because they're just one a permutation of the other, they are not. Like here is, 0.1, 1, 10, and 10, 0.1, 1. Because the C, the boundary component C is secretly A times B, and I'm confusing things there. That's the choice. Now, why do we have this wide variation that thinks that it is not that clear that goes to a Gaussian? Well, the thing is, when you go to long enough words, and computing the length of already words of length 100 is time-consuming for my computer abilities. What happens? I cannot do more than 100 in a reasonable amount of time. But if you go long enough, these bumps are around multiples of tens here. So when the word length is long enough, they're going to disappear. The multiples of 10, you don't see them. So basically, this happens because and in small word length. When the curves are really long, a difference of a small multiple of 10 is nothing. And this was proven. It was so nice, we did this thing, years ago, and it was proven in 2018, and it was proven in a more general way, like in a hyperbolic surface with certain constraints. This is Goldman, Taylor, and Tiozzo. This distribution is indeed a Gaussian. And then they even make it more general. They prove it for a large class of groups and and manifolds. And for instance, so one of these instances of their theorem, if you have a geometrically finite hyperbolic 3 manifold, and no, this is any manifold, and any generating set, they can find another generating set. The generating sets are the cuts I put in my original surface, and saying that yes, the length of the word goes to a Gaussian with a certain mean and standard deviation. The standard deviation could be 0 in this case. It's all concentrated, but otherwise, it's a Gaussian, which is, I don't know, fantastic. This is kind of recent, or I learned it kind of recently. Okay, so now I'm going to change gears, and I'm going to, I could keep in this stuff. I have more theorems and little things, but let's go here. This is slight change of gears. If you're lost, you can, if you want to recover, you can recover here. So this is a structure on surface, very appropriate to this conference, that I really like. So here we have a surface, and now my surface has an orientation, and it can have or not boundary. And I'm going to look at the set of free homotopy classes, and I emphasize the word set. Remember that pi 1 is the fundamental group. But if you look at free homotopy classes, these are a set. There's not a priori nice operation we can do on them. And I'm going to look at linear combinations of this set of free homotopy classes. These are just formal, final linear combinations. And for instance, if you look at something like here, which is curve, the inverse of a curve plus 2 times, this is a class, the inverse of a class minus 2 times a class plus 3 times of the trivial loop, this is an element of my vector space. And the inverse doesn't cancel with the non-inverse. So now I'm going to define a certain bilinear map first on this vector space, on this set of linear combinations. And then what I can do, of course, is take 2 elements of the basis and tell you which linear combinations of free homotopy classes do I get. So here I have, one curve in my class, and here I have another curve in my class. And so I'm going to choose, well, I have to choose representatives. I'm working with classes, and I'm going to choose them so that they intersect in transversal double points. In this example, there's 2 intersections. So each intersection point will give me a term. And a term is, again, a certain coefficient and a free homotopy class. So what do I do? Well, I go to, let me just, one more thing, here. I go to an intersection to see the term given by, sorry. I need to put a little sticker on my thing to point. So I go to the intersection point, and that term I consider, and I go around one of the curves, come back, and then go around the other curve. And this is the same as doing this little surgery at the point here, where I do the surgery by I erase my point and reconnect the branches following the arrows. And then I do the same thing with the other. Oh, and I put a sign, just comparing the orientation of these 2 tangents here with the orientation of the surface. Here, and I'm going to have an orientation of the surface has to be oriented. So this is the bracket. Any question? What do I have to prove here? I'm saying this is a bilinear map on this vector space generated by free homotopy classes. Are you sure it's a bilinear map? I define it on the basis, that's fine. I have to prove it's well defined. You all failed. No, sorry. I define this by, going to a class and choose a representative. Every time you choose in math, you pay. You have to prove it's well defined, or you are condemned to the math hell. So important thing. This is done, and in this bracket, is done combining two operations that we know well, which are, the loop product, which of course in free homotopy classes I can do, but I'm going to each place that I can do the loop product, and there I perform a product, and the intersection, so these two things are merged together in this operation, and it's well defined, as I said. So, and here is a cartoon of the proof. So suppose I have, this is a pair of free homotopy classes, and these are one pair of representative and another pair of representatives. And I'm going to move them through a homotopy together. But these pictures are going to change. The picture is going to change only in little disks, where the change is you're going to go to a picture like this, to a picture like this, and same with the other two. So, and of course the colors can be, different. And then you prove, so it's not hard to see that if you compute the, put in the appropriate arrows or put in all possible arrows, if you compute the bracket corresponding to this point and then the bracket corresponding to this point, they are going to cancel. So then when you move, from here to here, there's not going to be change in the bracket because the only change was this, and the bracket doesn't change. And the same thing with the others. The bracket doesn't change from one picture of the cartoon to the next. Therefore, the bracket is well defined. It's the same at one side and the other. So here is again the picture. Why do I have it twice? Oh, well, it's well defined. It's skew symmetric, and it's skew symmetric on the nose because to the I didn't say that maybe as slowly as I should, but you put a sign plus or minus 1 comparing the two tangents, the oriented two tangents, with the orientation of the surface. And of course, the tangents, they have to be ordered by the way they come in the bracket. So the order gives me the sign. So if I flip, I get the opposite sign. And it satisfies the Jacobi identity, which you can ask me at lunch. It's a nice proof, but time is always finite, so I'm not going to do that proof. And in this case, one could check that these two terms, these are different free homotopy classes. They don't cancel with each other. The bracket is non-zero. And wait, I'm not going to prove that, but trust me. And here is one thing, now we can go back to my previous talk, my previous half an hour, which is that, one can see that, remember that we study intersections and self-intersection points as subwords, as pairs of subwords. Now, if I have an intersection, remember the bracket of, the bracket is a sum over intersection points of two curves. So, but intersection point is a pair of subwords. And a pair of subwords is going to tell me where can I cut. This is a cyclic word, and this is another cyclic word. So they are, they have an arrow, they are oriented. So I have my two cyclic words. And my cuts, if I choose a pair of subwords that give me intersection, this is like choosing two places where I can cut. So this one is here. So I cut my cyclic word 1, and using my other subword, I cut my cyclic word 2, and then I reattach them. And this is the same that we did with the curves. The intersection told me, cut your curve here, cut your curve there, you get two loops that are open and directed, and then you reattach them. You do exactly the same thing in the discrete universe, done by the word. So, so this is the bracket, and again, the lovely thing is that you can put this in a computer, and I did. Now here I have an example with the curve that we looked at, where I'm taking the bracket of this purple curve with a pink curve here. Well, these are It should be one is orange and one is red. But each intersection point, well, you know, this is like a ring of one thing, so you cut it, no more choice of what to cut the word B. But you know, you cut this, and you're going to intersect small b here, and of course you're going to cancel with a big B. Then you intersect, you know, you insert B here, and so on. So each intersection point gives me a place where I can insert little b. So now I have that presentation. And I was intrigued, you know, like, well, in the previous case, we know that we have two curves that intersect exactly twice, and the bracket has exactly two terms. It's always like that. So, well, how am I doing that counting? So, well, we use this, I call the Manhattan norm. Manhattan is in mostly, you know, square. So to go to one place, you have to, you know, tack, 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 tack. So this is equivalent to do the sum of the absolute values of the coefficient. This is the, you know, real count of how many terms. I want to study the relation between these two numbers, the number of terms and the intersection. Anybody want to risk? So how they relate. So remember, the bracket is a sum over intersections. And I can choose representatives. So I'm going to start with two representatives that intersect in the smallest number possible of points. So how many terms I'm going to get when I compute the bracket? Well, exactly as many as the smallest number possible of points. Of course, I may have cancellation. You know, there are signs, and I'm taking classes. But at most, you know, I get that. So this Manhattan norm is bounded by above by the intersection number. And this is what I just said. And I was wondering, is it equal? And I mean, in fact, you know, we have an equivalent statement with my collaborator, and we tried for a year to prove that it was equal, not this, with another operation, but it was similar, and we couldn't prove it because it was wrong. That was pretty good that we couldn't prove it. And I found, you know, even if it's not too hard, I'm going to give you the examples, and I'm going to say, oh my gosh, these people are dumb, but tough luck, you know, we are not promised, but we couldn't find examples until I put this in the computer. So here is one example. Now let's look at the, you know, the pair of pants, and the cuts are equivalents to just take these two generators. Here is A and B in the fundamental group. So here I have two curves, and they intersect in 2 points, you know, a green and a yellow. Seems like the theorem of this talk is every pair of curves intersects in 2 points. So now I'm going to compute the bracket, and so this is the yellow point. The yellow point, I have to go this way, yeah. So you go here, and you're going to do A, B. You come back here, and then you're going to do B, A. So this is the word. You have to look at it as a cyclic word corresponding to the yellow point. And if you do the one for the green, well, it's quite similar. It's BAA, AB. And this should be a capital B. I don't know why it's a small b there. Well, these two as cyclic words are the same. And the signs, you can check, are opposite. So the bracket is 0, but the intersection point is 2. These points, you know, there's no way to remove them. So that was it, not equality. So, but when there's equality and everything is a question that I'm interested in. So now here is a mistake that appeared in this. I should have said it. I wrote it, hopefully, that this bracket is due to Bill Goldman, which he was studying representations of the fundamental group of a surface into Lie groups, and he found, you know, the preimage of this Lie algebras that you have in these Lie groups. Anyway, so go on. So here is a piece of, you know, Bill's paper, and he wrote at some point, famous last words. He says, and this times this is equal, and this is minus this, as clear from the picture. Quite dangerous. So I was trying to understand his paper, and I was checking this, and it was not giving me minus, and then but totally the opposite. Then I put this in the computer. So let's do this quickly. I'm going to compute the bracket of x and x bar, where this is x, okay? So I thought I put it here. Oh yeah, here it is, x and x bar. And I don't think I put points, but anyway, let's just do it. So let's look at this point. So if this, I'm going to compute the bracket corresponding to the point I'm pointing. So this bracket is, so you first go, run around A, and then B. So I do A and B, and I come back here, and then I go this way. So this is, sorry, did I do it right? I'm doing, this is A and B. Is it a capital B? Yes, it's a capital B, right. Okay, good. And then A. No, this is a small b, no? B. And then I'm going here. And then A bar, B bar. So this is small b. AB, A bar, B bar. Now, if you do the other one, you should trust me or just do it yourselves, is BA, and this is a cyclic word, a ring of letters, BA. So these two in particular, they're one the inverse of the other as cyclic words, and they don't cancel, and if you look at the signs, they're opposite. Whatever orientation I put, this sign has minus this. So this curve has one intersection, but when I look at the bracket of A bar, I get two terms. And what happens is that every time I do this, I will get that. So here I have a curve with, two self-intersections. And each self-intersection, if I'm double the curve and running around, I get this little square here where these are the two intersections, and these are the self-intersections of the duplicates. Pairs are the bracket corresponding to this and the bracket corresponding to this, they have opposite signs, and one is the inverse of the other, and they never cancel. Not this with this, and not anybody with anybody. I was counting how many terms this has. Wasn't doing. The computer counted how many terms this thing has, and it's always twice the number of intersections. So not only wasn't zero, there was never a cancellation in this particular situation. And I tried to prove it, and this is a long time ago, never succeeded. Now recently, like I think in April of this year, this paper appeared where they prove this special case. I joined forces with one of these co-authors, Miguel Paternal, there, and we tried to prove it. No success, but they finally managed to prove it that this, if the bracket of x with x bar is 0, then x is simple. And this is a proof for people who like geometric group theory, because they use a lot of their tools. Let me just, let's see, a little more. So let me go to the past. So I was trying to, count the elements of the bracket of x and x bar. Couldn't prove it. So I was working, the grad student, Fabiana Kronkel, and she said, why don't we take instead xx squared or xx cubed and see what happens? And again, the computer says there's no cancellation. So if you compute the bracket of x, if you put, x and then put a copy of x cubed running around, they intersect, 2 times 3, the self-intersection number of x. Imagine all these copies running around. We did prove that. We couldn't do it with 2, we did it with 3 for surfaces with boundary. The proof is I mean, I can't believe we did it. It's incredibly painful because it's really looking at the words and comparing small cancellation. We're using this idea, and it says, because it was, ugh. And later, I joined forces with Siddhartha Gachil, and what we prove, I'm going to tell you, a little bit of a very cartoonish version of the proof, and with hyperbolic geometry, which is, I think, a very much nicer proof. And what we prove is that we need to P and Q, one of those to be large enough, so then the Manhattan norm of this is exactly what it should be. I mean, there's no cancellation when you go around enough times. And I have time to show this is one of my favorite proofs. You probably know this, or some of you, but I'm going to do it anyway. Do I write? No. Well, yeah, I should write. So here, what I'm going to show is this lovely result, that if you have, this is the Poincaré, so we have in the hyperbolic plane two hyperbolic transformations whose axes intersect. The intersection point here is P, and I'm going to prove that if I multiply these two transformations, I get another hyperbolic transformations, and the axis, I can tell you what it is. So to do this, we take, this is my intersection point P, and I'm trying to do blue times red. So I'm going to mark a point from P going backwards. Remember, the axes are oriented, half the, I put it TA, so the blue is A, half the translation length of A. So, and then I'm going to put, again, from the intersection point, going forward, mark a point which in half the translation length of B. And now I'm going to write the transformation A is, I'm going to reflect, let's see, how is it? 180 about, if I have to do P, reflect 180 about P. I've written that down. It always takes me time to think. I think this is reflection 180. So if I reflect 180 about S, I do. If you look at this, just look at it with S, it goes exactly the translation length of, this is A, the blue, the transformation with the blue axis. And the transformation with the red axis, B, is RP, R. So again, this is rotation 180. So this is RP, RR, RS, which it's hyperbolic, and the axis is exactly the line passing through S and R. This is very neat. And why do I need that? Because now I'm going to use this for my Goldman bracket. So now, imagine that I have my two curves, and imagine these are geodesic on the surface, and I'm going to lift them. And let's just take a full lift. Here is the intersection point P, and this is the projection. And this is one lift, a full lift, and full lift. So this tells me, well, the product, the axis is here. Moreover, if I lift, imagine that I'm going to lift, I'm doing this little surgery that we do to compute the bracket, and I'm going to do a full lift of the thing without the representative I get, which is a quasi-geodesic. It's a geodesic, but I have, in two places, I have to do an angle. You have to imagine that you go in a little car over your geodesic, and when you arrive to the intersection point, you have to turn following the arrows. You're in the blue, you have to turn a certain angle and go to the red, and same with that, when you're in the red and arrive to the intersection point. So, though this is so I take the full lift of this thing after the little surgery, I get that. And these two magic points, and here is a point that I really like, well, I can look at them in the surface. And what are these points? So this is a point that is, so if I look at this point here, this distance from the intersection point up to this big point is the same, the length, not the distance. The length of the curve from here to here is the same as the length from here to here. Sorry. The length from here to here is the same as the length from here to here. And this is again, the half length. These 2 points, if I remove them, I get 2 pieces of the red curve of the same length. And now we know that there's a closed geodesic passing through these big points, these magic points that are marked, and that's a geodesic in the term, in the bracket term, corresponding to this intersection point. And so here is a representative. Well, I've just wanted to play, and I put this should be the geodesic passing through the term corresponding to that intersection point. And here is a proof. Here we have what happens when I let p grows. So I'm taking a larger power of x. So this little wiggly thing, the zigzag curve we show it, is going to have pieces that are very long when p very, very long. Now what happens if you have a cancellation? You're going to have 2 terms. Well, that the free homotopy classes is the same. If the free homotopy classes is the same, the geodesics are the same. So I can consider 2 zigzag curves. So if I'm going to have lifts, pair of lifts. I have one lift, this is the axis, and I have my zigzag curve, and I'm going to have another zigzag curve, shadowing the same axis. But now, if I make p very long, one of the zigzag curves, both the zigzag curves are going to have very long pieces. And these are very long pieces of a geodesic that they are going very close. And if they're very long and they're going very close and you're in the hyperbolic plane, you have to be the same. 2 geodesics that go for long time at bounded distance are the same. So this is the proof, but the essence of the proof of the xp and sq, and there's no cancellation when p grows. But, okay. And then I'm going to finish. Okay. I joined together with a student, now a student of my former collaborator, this is Arpan Kabiraj. He proved this nice result, and he observed, it's an observation, but somebody had to do it, and it's very clever of him to do it, that every time you have cancellation, the intersection points, 2 intersection points that cancel, they have the same angle. So when you fix the metric, you vary the metric, they vary together. So then we use this. This tells you that every time you have a cancellation, there's some symmetry. And here we have, for instance, I was trying to see why, this is, maybe I should finish here. This is another former student, Matt Gecking. I should have put his name here. Thought I did, but anyway, I'm 57. So this is a pair of pants, lifted to the Poincaré disk. So here we have, you glue this blue segment with this blue and the green with the green, and you will get a pair of pants. And he did this fantastic app that you can ask me. You can play with it. You can put curves, and it draws the geodesic, and these are the parameters of the metric. So here I draw 2 curves. They are here like AB, capital A, B, B, etc. Whose bracket has a cancellation. And it's kind of weird because this cancellation tells me that there are pairs of points. There's a pair of points that when I vary the metric, they always have the same angle because they cancel all the time. Anyway, I'm over time, so I'm done.
Thank you, Moira, for this talk. Now is the time for questions. I have to run.
Thank you for the talk. So it's a question about the first part, the counting intersection. So when you have this Gaussian picture, it's tells something about the middle of the array somehow. But if you look at the extreme left, we have this polynomiality, right, in column.
You have what?
The polynomial growth of the numbers. Because if you look at the number of curves with zero self-intersection, you're counting like simple curves. So you get polynomial growth, and it's true for any column, right?
Mm-hmm.
And yeah, that's Mirzakhani or Riven argument. And do you have a transition, like going to this polynomial growth to the actual exponential growth, something more like large deviations going to the left hand of the array? So that's one question. And the other one is, what do you know about the right-hand side of the array? If you look at curves with, let's say, close to L square intersection, like alpha, close to the maximal possible number.
Yeah.
How the right columns, like how do they grow in the array, if that's clear?
Well, I mean, everything, I mean, it was proven, I think Mirzakhani, in fact, when I put, Maria Mirzakhani wrote me, I had conjectured that this growth, let me just put the table that we're looking at, so we get inspired. This is not the picture. So if you look at the, so you're saying this is a polynomial growth. Each column is polynomial.
Yes.
Each column is polynomial.
Yes.
And she proved it. Riven proved for 0 and 1, but Maria Mirzakhani for all self-intersection number. No, sorry. Let me erase. Mariam studied this for geodesic length, so length in the geometric setting with constant negative curvature. This is world length. Now, she did suspect that this was right. We had an exchange. And Vivica Erlandsson, that's the last name, looking for advisor, yes. Sorry, zooming out. She did prove it in general that this is a polynomial, and the polynomial depends on the number of elements in the fundamental group. So this is combinatorially also happens. Now, if you look at the maximum, I don't know if you're asking about this, I can look at how many I have here, in the cells, how many I have with the maximal, and this seems to be polynomial too. In the case of the pairs of pants, now in the case of punctators, I can prove it. How many curves you have with the maximal, it's also polynomial with same degree. In general, I suspected, but I don't know.
Okay, thanks.
Other questions?
In the distribution for length, you had also a Gaussian, and the mean, it depends on the parameters of the metric, like the cuff lengths of the pants.
In the geometric length.
Yeah.
Yeah.
Yeah. Yeah. Well, somewhere you said that the two parameters of the Gaussian, the mean value and the standard deviation, they depend on ABC.
Yes.
And do you have ideas of how to extremize, for example, the mean value, which ABC give lower or bigger mean values?
No, I tried a little bit, but no, but I would like to know. So I can pass you my program and you experiment. Yeah.
Thank you.
Oh, while you run there, I have an announcement. Forgot. So we were going to do this show and tell, in Americans, but they like to speak in public. So in kindergarten, they do these things about show and tell, and you have to go to your class and take a toy and explain the properties or whatever of the toy. So I thought, let's do a show and tell here with some math things. I just saw one of these wonderful tori, there, and so we can take all math toys it's in the second, after the afternoon talks in the middle, we can start doing a show and tell, and if there's an overwhelming interest, we keep doing it, but we meet here, or at the coffee break, we start with a show and tell, so whoever has any math thingy, bring it and we chat about it. Sorry.
No, it's great. Any other questions? Yeah.
So your whole construction was always on a pair of pants with boundary. So the boundary was kind of a critical part. How much of your work can extend to surfaces without boundary? Like, what if you did the same construction just on the torus?
Which one? I mean, anything can be done, by the way. It's like, I mean, for the part of this intersection, self-intersection, I should have said a grad student, I have jointly with Dennis Sullivan, he did prove that the same theorem that the distribution of self-intersection, sampling by word length is a Gaussian, also works with closed surfaces. You have to pay, it's kind of expensive because, you don't have the bijection, and you have to be careful because certain words, there's no word to get the shortest word representing, but it works with closed surfaces. And the result about this, the result of, Piozzo, Taylor, and Goldman also works, in very general settings. It's easy to compute with, but, I should have said that. Thank you.
Super, thank you.
So maybe we should go have a coffee break, just because it's my fault. I gave you 1 hour, which was great, but it was only 50 minutes. So,
whoa,
my bad.